Okay, so
I think
I just
before you start, so one of us, and I suggest that you do it, should present the problem. So it's not just a solution without any context. So maybe you could first say what the problem was. Quite easy in this case.
So the question was to prove the Jacobi identity. So I choose to do a straight, a direct proof by expanding all commutators. I'm trying actually to find the exercise. Okay, so that was the question. As I said, I expand each commutators, and then I recognize that each term, like ABC, we have minus ABC on another side, so each one of them cancels out, and we have 0 at the end.
So you essentially do just a matrix expansion. It's just matrix multiplication, and you see that the terms cancel.
Yeah.
Yeah, that is indeed the intended solution, and I think you see that it's entirely straightforward. You have to use one trick for the no, sorry, you just write everything out and it cancels as it should. Yes, good. Any questions to that? No, I think it is completely straightforward. So in case you didn't get what the task was just to prove that this sequence of commutator at the top of the page is equal to 0, which it is. And this is the Jacobi identity, and this is the Jacobi identity for matrices. Okay, and then thank you, Lucas, for this presentation. So for problem number 2, is there anyone who's willing to present that?
Yeah, I can collaborate on that.
Great.
Okay.
So I guess you want to share a screen, or how do you want to do it?
Yeah, I think I have to share that one.
So we have seen that should work fine.
Yeah. So you have to see the pink screen, I suppose.
So I think it's good if you present the solution in some detail actually, so that people can try to follow the steps.
Yeah.
Let's first start with defining the problem as well.
So you see the PDF, right?
Yes, we can see the PDF.
Okay, perfect. So the problem is to prove the Baker-Campbell-Hausdorff formula, which looks like this. And we need to consider infinitesimal generators of the form epsilon A and epsilon B. And we only need to prove this to order epsilon squared. So this makes things a lot easier. If we go to the pink screen here. Okay, so we define those generators epsilon A and epsilon B, and we need to prove this thing over here. So we write out e to the power of A as e to the power of epsilon A, and we expand it as a Taylor series, where this thing over here is how I write the identity matrix. So we start off with the identity plus the usual exponential expansion to order epsilon squared plus some higher order terms. And we do the same for e to the power of b as well. So we again expand it in the exact same way over here. Then we multiply both things, EA and EB, and see what we get. Okay, so I just take those two expressions and I put them together. I expand, and so term by term. And I only restrict myself to order epsilon squared. So terms like these two are not present, for example. Then I just collect some terms and order them according to their powers. So identity plus things of order 1 plus things of order 2, and so on and so forth. And I just put it in some nice form. Then I stopped here because I didn't quite know what to do afterwards in order to prove the identity that we needed to prove. So I just started from the right-hand side of that identity, and I started to work with that. And I also restricted myself only to this term, and then I didn't consider the rest because the rest would have given me a higher order epsilon. So I just started to expand this part over here, which is a bit more lengthy. So again, a Taylor expansion, we have the identity plus whatever the exponent is, plus a half the exponent squared. And this is as much as we need. So I should have put an approximate sign here, actually. Then I expand the commutators here and just perform the multiplication in the parentheses. Then, well, here I perform the multiplication inside term by term. Most of the terms end up being higher order, so we don't even consider them. All that survives are just a squares and things. Well, a square was really epsilon a, so this would be of order epsilon squared. And then I just expand the parentheses as well, cancel out some terms that have opposite signs, and then bring everything to the same form that I had for the expression on the left-hand side. So we see that this is of exactly the same form as the thing that we saw above, which I think proves the identity up to second order.
Yes, very good. So it was actually a fairly straightforward exercise as well. It was just expand to second order in epsilon and see that the same expression is obtained on both sides. Yeah. So I like to stress here as well that the point of the Baker-Campbell-Hausdorff theorem is that if the commutator stays in the algebra, then the nested commutators will stay in the algebra, and so you will have a group, an element in the algebra. So this theorem allows us to make connections between the algebra and the group elements. It's not super hard to prove, but it's also not that easy, so we are not going through the full proof in the course. Yeah, any questions or comments? The next problem, problem number 3, was supposed to be solved by someone from group 2. So that's Luca, Joshua, Martin, Samyak, Adam, and Asha. So is there anyone who wants to present problem number 3? It's also a fairly simple problem. Okay. If there's complete silence, then I will do it. But it won't be great because I'm not prepared, but I take the occasion then to expose you to an experiment. So I will use the board here. See if this quality is readable. So I have a tiny picture. So it used to be readable, but the lighting has changed. So maybe someone can tell me if it's still readable.
It looks all right.
Fine. Someone is, Sunny is indicating that that might be the case. Okay. And I'm in picture. Good. So here, the point of this task is to prove that if we rotate an element in the Lie algebra, we are still in the Lie algebra and we still obey the same commutation relations. So what we want to do is to prove that PA commuted with PB. Let's see. This just looks perfectly readable. I have a tablet as well, so I can check it. PA commuted with PB. This is in the physicist's convention. I some structure constant FABC PC. And now the point is that we should prove that if we take the PA's and we rotate them, so that the PA goes to PA prime equal to E of alpha, but this alpha somehow parameterizes the group element. PA E of alpha inverse. We should prove that this Ti prime satisfy the same commutator, so this guy. And this is actually pretty easy to prove. So all we need to do is to rotate both sides of this identity, and then we will insert a little 1, and then we will see that we can recover this identity but with prime things. Okay, so I rotate here. So I then have E. I could write D of alpha, but I dropped the argument of alpha and I just write D for simplicity. So D A commuted with PB E inverse is equal to I FABC, constant I just pull out, D BC B inverse. So it is this relation up here multiplied from the left and the right with D and D inverse. And constants I just pulled from here. Okay. So I'm already happy with this side, but I want to work with this side. So what I do then is that I write it out. So this is D, PA, PB, D inverse, plus minus rather, D, PB, PA, D inverse. So I just written it out. And then I insert 1 in the form of D inverse D here. And I insert it here as well. And then I stare a bit at the expression and I see that this thing here, this is nothing but my PA prime. And this thing here, this is nothing but my PB prime. And similarly, the second part from the commutator is nothing but my PB prime, PA prime. And looking over here, I see that this is already my PT prime. So I have the PA prime, PB prime minus PB prime. PA prime is I F A B C PT prime. And now this here is of course nothing but the commutator between the A prime and the B prime. So this equals to this proves the identity. A DB is IFABCDD with primes everywhere. So that was also a completely straightforward exercise. Questions to that? So I see my tablet here and it looks readable, but could you hear me as well? Because I was far further away from the mic than normally.
You were audible,
So,
yes, we could hear you.
Someone was, Christina is nodding at least. Okay, good. Then let's move on if you don't have any questions. Problem 4 is also comparatively easy. So it's about the generators of special matrices, so matrices having determinant 1. Task is to prove that those matrices are generated by traceless generators. So did anyone do that problem? If not, I guess I'm solving it myself. Okay, so diagonalizable matrices are generated by traceless matrices. So it's written here that the matrix should be diagonalizable. So we diagonalize the matrix. That means that the matrix has its eigenvalues on the diagonal. So we have some lambda 1 to lambda n on the diagonal, and we have zeros everywhere else. Now, to generate this matrix is easy. It's just e to the logarithm of the eigenvalues. So this is e exponential of log lambda 1 to lambda n. Barely readable, but yeah, lambda 1 to lambda 1. And since we want determinant to be equal to 1, this means that the product of all these i's e to lambda I must be equal to 1. Determinant is not just the product of the diagonal elements. And this means that whatever that the stuff I have in the exponent must add up to 0. So this implies then that the sum over I log lambda I is equal to 0. So what should we call it? Call it lambda without an index. So lambda is traceless. Lambda is traceless because the sum of the eigenvalues, the sum of the diagonal elements must be 0. So any questions to that? Then actually for problem number 5, so this will be an identity that is encountered later on in the exercises here. And actually for problem number 5, which is a rather important problem because it's about counting the degrees of freedoms that we have for the various groups. Someone actually did offer to present that.
Yeah, I would like
so
to
maybe
present
Hector can prepare himself while I'm moving back.
Can you see my screen?
Yes.
So in this question, we were asked to find the number of free parameters for the different for a number of different groups. So if we start with the general linear group with real elements, we have an n times n matrix, which means we have n squared real elements. So we simply have n squared parameters. While if we have complex elements, each element is we have n squared complex elements, but each element has 2 real parts, so we have 2 n squared parameters. Then we have the special linear group, and this is a subgroup of the general linear group. So we have n squared parameters from before, but we have one constraint that the determinant is supposed to be 1. So then we subtract that constraint to get n squared minus 1 parameters. This one constraint allows us to express one parameter in terms of the others. In the same way,
Hector, so this is all good and right, but there is one point that people may find confusing here. So for the first general case, we had that the determinant should not be 0 at least, because we should have an invertible matrix for the definition of the group. Somehow that didn't change the degree of freedom counting, while requiring that the determinant should be 1 did change it. Can you comment on that?
I'm not sure. I can't remember. I think I just forgot to consider when the determinant is not supposed to be equal to 0. But so I don't actually remember why it doesn't remove the number of free parameters.
So I recall people being confused about this 2 years ago when we did this exercise as well. So the point here is that having determinant equal to 0 is a 0 set. So pretty much any random matrix that you pick will not have the determinant being 0. So therefore it doesn't enter into the degrees of freedom counting. But requiring the determinant to be 1, well, any typical matrix that you pick by random will not have the determinant 1. So it's a constraint that you will have to impose, and therefore it does enter into the degrees of freedom counting.
All right.
Yeah, but please go on.
Yes. And then after this, we were supposed to find the number of parameters for the unitary group in n dimensions. So we have 2n squared. This is a subgroup of the complex general linear group. So we have 2n squared parameters from there. And then we know that an element G times its Hermitian conjugate is supposed to be equal to the identity matrix since it's unitary. And written in terms of the components, we have Gij times G Hermitian conjugate JK. And then if we take the transpose, we split the indices. It's supposed to be equal to the Kronecker delta. When I is equal to K, then we have this sum over J here is supposed to be 1, and I can take n different values. So this is n constraints. We have n columns or rows that have to be normalized to 1. If I is not equal to K, then this is supposed to be equal to 0, and writing each element in terms of its real and complex parts and multiplying it out, we get 2 terms here. So this first one is a condition on the real parts have to be orthogonal to each other, and the other one is that the complex parts have to be orthogonal to each other. We have n rows or n columns, and each pair is orthogonal. So each part contributes with n choose 2, because we have n rows and we choose 2 rows to be orthogonal to each other. And then we can just put these into the binomial expression to get n times n minus 1 over 2 constraints. But this is only for each part. We have that the real parts should be orthogonal and the complex part should be orthogonal. So we multiply by 2 to get n times n minus 1 constraints from this. So then 2n squared minus n times n minus 1 gives us n squared parameters, which is the number of free parameters for the unitary group.
Very good. So that's a result to remember. N squared parameters for the unitary group.
And then
Here we go special.
For the special unitary group, we in the same way as before, we simply only have one extra constraint on the determinant, so we get n squared minus 1 parameters.
Yep.
And then for the orthogonal group, we calculate the number of parameters pretty much in the same way as before, as with the unitary group. Now we have n squared instead of 2n squared parameters from the general linear group, and now we only have that the transpose times itself should be equal to the identity matrix. So in the same way, we get that each row or column should be normalized. So that gives us n constraints. And now, since the elements are real, we have the same thing as before, but we only get one of these n over n minus 1 over 2 number of constraints. And then if we subtract them, we get n times n minus 1 over 2 parameters. And then for the special orthogonal group, we only have an extra constraint with the determinant, so we get n times n minus 1 over 2 minus 1 parameters.
Yeah. So let's see, was that all that was asked for? Yes, it was.
Yes.
Good. So actually for the next exercise is the same exercise, but it's supposed to be done at the level of the algebra instead. So of course, counting degrees of freedom at the level of the algebra or counting them at the level of the group elements, we should have the same thing, same degrees of freedom. So is anyone willing to present a solution to problem number 6? So actually, when I started my part of this course, I asked if the exercises had worked. So I will consider this as not quite working. The intention was that you should be prepared to present the solutions. Fadi has applied this before, but not me, and it has worked great for him. But okay, it was before COVID-19, and it was with a different student group, many good master students and PhD students. But I wish you had told me, because in my opinion, this could be done much better than how it's currently working. So you also have the responsibility to make your education work well. You have a responsibility for each other in this case. Okay, so I then take it as no one solved that exercise. And no one wants to present it as well. So then let me expose you to another experiment. So I will now experiment with sharing my tablet instead. Good, so now you should be able to see my tablet. So the first task is then to count degrees of freedom for SLNF, where F is either R or let's see. And other groups will then, the degrees of freedoms from other groups can be obtained by the degrees of freedoms that we get for S, L, and F, and further restrictions. So sorry, I should start with D. G, L, and F, and then I should move on to S, L, and F. So this part of the exercise is actually working exactly the same as when we considered it at the level of the group. So we just take any matrix and exponentiate it, and almost always, so except for zero set, it will be invertible. So again, the determinant, the condition doesn't enter. So we just get, for a real matrix, we have n squared degrees of freedom. Or for complex matrix, we have 2n squared because we have 2n degrees of freedom. So twice as many, one complex and one real part for each element. Okay, so that was D, L, and F. And then we have special, as I said. So now we have to impose the determinant being 1. And that implies for the reals that we have 1 degree of freedom, so it's n squared minus 1, because we subtract 1 degree of freedom for the determinant condition. For the complex numbers, we have 2n squared from up here, but then we also subtract 2 degrees of freedoms, because we have a real and an imaginary part again. So this is 2 times n squared minus 1 for f equals to c. And then we make further constraints here. So we now want to have the unitary group. So un. So the set of complex unitary matrix, let's start with that. Then let's have a look at the form of the generators. Maybe let's start with that first. So we want that G dagger should be equal to 1 for the G's in U. So if we expand this out to lowest order and write G as e to alpha x for some generator. So I'm here taking the easiest way out, and I'm using the mathematician's convention, and I'm not inserting an I in the exponent as physicists would normally do. We could solve the problem in exactly the same way with an I. It would be, we would then obtain Hermitian generators instead of what we will now obtain. So let's expand this out then. So G is then 1 plus alpha x, D dagger goes to 1 plus alpha x dagger. And this should then, to lowest order, be 1. So it should be 1. So the terms, the linear terms in alpha from here must cancel against the linear terms in alpha from this second expression. So I get that x plus x dagger must be 0. Or 0 n times n matrix if you want. So we have that the generators are anti-Hermitian. So I reminded that with the physicist convention, if we would have an I up here in the exponent, we would have Hermitian generators. Without the I, we have anti-Hermitian generators. Okay, so now we have this plus this should be 0, and we need a new page. So let's see what constraints we get from that. So we have anti-Hermitian matrices. X dagger plus x is equal to 0. So clearly that implies that the diagonal elements must be equal to 0. And this gives us n constraints. Then if we consider the matrix of this form, so we have some diagonal and we have some upper triangle. This constraint, knowing this triangle, is fixing this triangle. So we must count how many degrees of freedom we have in this upper triangle. And in this upper triangle, we have then, first we have half of the remaining elements once we have subtracted the ones on the diagonal. So if we start with n squared element, and then we subtract the diagonal, that is n, and then we divide that by 2, then we have the number of elements in this upper block here. And if we have complex matrices, then we multiply this with 2. So we have 2 degrees of freedom for each element above the diagonal, say here. So collecting pieces, we then have that the dimension of un, as in the algebra un, is equal to what we started with, 2n squared minus n minus the 2's cancel, so it's minus n times n minus 1, and that is equal to n squared. And that was also the result that Hector obtained before. So we have n squared parameters for un. Then we will make further restrictions. So this was un. And then we move on to SUN, or maybe I should write with small letters to indicate that it is the algebra. So SUN. This works exactly as when we treated them as matrices. So we had before n squared, and then we subtract 1 for the determinant. Yeah. And now this is the number of degrees of freedoms. And then we move on to the orthogonal group. And we consider its algebra. We can do this. Let's see. Now, the task was to do it just for the real numbers, right? So let's do it just for the real numbers. But we can reuse the counting that we did before with respect to upper elements in a matrix. So we had before that we had n times n minus 1 over 2 elements up there that we will use. And we have here the constraints. So if we expand out as we did before, so let's see if I can go back to that board. Yeah, we have it. We had this constraint here. X plus x dagger should be 0. Now, in our case, this x will just go to x transpose because we have real matrices. So we then have that x plus x transpose should be equal to 0. Okay, so then we subtract degrees of freedoms as we did before. So we then start with n squared. Then, given the upper triangle, the lower triangle is known. So that removes n times n plus 1 over 2 degrees of freedom. So collecting this, we have n times n minus 1 over 2 for the orthogonal group. And then we consider the special orthogonal group, real matrices. Here we note, however, that this matrix must be antisymmetric because of this constraint. So we already have that the diagonal is 0. So antisymmetry is imposing by this constraint here that the diagonal is equal to 0. So no further restriction in degrees of freedom. The additional degree of freedom that we have for OM is not a continuous parameter. So SON is all rotations. Always. Okay, any questions to that? Okay, so then we move on to the next problem. So what about problem number 7? So can anyone present the solution to problem number 7? Actually, what we should do respectively is to take the break. So I see it's 3 minutes past 11. So let's take the break and then continue with the problems afterwards. So yeah, feel free to take the break. But if someone is still in front of the computer, I'm really curious to hear how it worked for Fadi. Because I really anticipated you to be prepared for this. So no one feels inclined to comment.
Well, with Ferdi, basically, I don't think that people worked in groups, and just he asked if someone had solved it, and then someone presented it most of the time. And in case no one had solved it, he just showed the solution.
So it was his idea to make it this way. He thought it would work out because he had very positive experience with it from before. But I guess the major reasons why it's not working so well this time is COVID-19. So you're not actually meeting each other in person. So you don't feel so responsible as you would otherwise. And the different student population, because it used to be a student population of PhD students only some 10-ish years ago. And then 4 years ago, we made it a proper course for the first time. And I was not involved in that year, but two years ago, it was 50% PhD students and 50% other students. And the other students consisted to a rather high fraction of rather good master students who went on to eventually become PhD students. So it was very good students. So apparently this year we have a different student population. So I know many of you that you're third year students, or yeah, some are fourth year students. Not so many PhD students. So it's a bit different. Okay, I'll take a break as well. So welcome back. So I think it would be nice to see some faces. So let's see here. I think the conclusion was that no one was prepared to present exercise number 7 about the center group. And I guess no one has changed his or her mind.
I could present it if you like. I just need to connect my iPad.
Okay, yeah, fine, great. Here we go.
Okay, so let's see. Should be able to share screen.
You should be able to share screen.
It's like so, right? You see my screen?
Yes, we see your screen.
Okay, so in this exercise we're supposed to find out the center group for these different groups then. Okay, so the center group is defined as the group elements that a set of group elements such that they commute with all other group elements. Okay, and then we had this hint, which was Schur's lemma. Okay, and Schur's lemma says that if we have an irreducible representation of the group, and we have some matrix that commutes with this irreducible representation for all group elements, then this M should be proportional to the identity. Okay, so then we sort of know that, okay, all these center groups should in some way be proportional to the identity, but then the question is how. So for example, if we start with U of n, we know that this is a complex group. So if we know that the group elements here, or the representation, has this property. So then we can simply write Ci and then C star. Okay, if we take that away around, it doesn't matter. Okay, then we see that this is the identity. And then of course we get that C squared should be 1. But since then U is over the complex group or a complex field, we can take a complex number that fulfills this. Well, we have this number for all angles that are in this interval. Yes. So for U, we have that the center group becomes Ci phi, like this. Okay, and then we do the same thing for Sun. Okay, but this time we have that the determinant of a group element U should be 1 as well. Okay, well, in our case that translates to the determinant of Ci should be 1. And then of course this becomes that C to the n should be equal to 1. Well, we know that the solutions in the complex plane for equation of these forms are given by C equal to Ei 2 pi k over n, where k runs from 0 to n minus 1. Okay, great. And then we have the orthogonal group. So O of n comma f. And here I see, I think I've only done it for the reals, but okay.
The task the intention was that the task would be only to do it for the reals.
Yeah, exactly. But there's an F in.
Okay.
But yeah, okay.
Then I should remove that. Thanks.
Okay. So for this group we have the same property as the unitary group, but for the reals they're basically the same thing. Then we get that C squared I should be equal to I. Okay, well, of course, if we're in the reals, we know that this only has 2 solutions, minus 1 and 1. So we have that the center group for the orthogonal is minus I and I. And then we have sort of the little bit more interesting ones, and that's SO2n. So now we also have that the determinant of the group element here should be 1. But here we have, there's an interesting thing that happens when we have an even number or an odd number. So we start with the even number, okay? Then we have that, okay, the determinant of this is equal to C2n. That should be 1. Well, there's no problem here. We can use both minus I and I. But if we have an odd number, then this, of course, becomes 2n plus 1, should be 1. But, okay, a real number to an odd power, that should be 1. Well, then we can only have the identity. So we lose this one when we go to special. And
Very good. Thank you. I think it was a very good and clear presentation. But you also had a device that not every student will have, so
yeah.
that helps. So any questions to that? This is how I hoped that it would work. Okay, for problem number 8. Problem number 8 is a very relevant problem in the context of quantum mechanics. So it is to prove that Casimir operator L squared equals to L1 squared plus L2 squared plus L3 squared commutes with all elements in the Lie algebra. So the same thing then applies to SO3 and SU2. And this is why we can label states in quantum mechanics with L squared and, for example, LZ. So this is clearly also really at the core of the course, and it's a quite important problem, but that doesn't mean it's a hard problem. It's comparatively easy to solve it. So we also had someone who volunteered to solve it. So that was Adam Warnebring.
Yes, I will draw on whiteboard. I don't have any pen, but I will try my best.
Yeah.
So I will use the hint that we have L squared. Let's just so we use the hint that L squared can be written as this, where we sum over I, of course. And then it's quite straightforward. If we take another element, Lj, and commute it with L squared, we get and from here I will use the hint in the problem text, which is expanding the commutator. So we get and from here we can use what's it called, the commutator for the elements. So this commutator here is I times epsilon j I k and then lk, and this time we sum over k as well, of course, and plus from this term we get And now we see that this is the same for both, so we can write this as and now we are more or less done because we see that this part is symmetric if we swap I and k, while this part is antisymmetric if we swap I and k, which means that for each term here with ik, we will get a minus sign where we take ki instead. And since this doesn't change under, if we swap k and I, we have something antisymmetric times something symmetric, which must be 0. Yeah, and that's, and of course it doesn't matter what j is because this is symmetric in all indices.
You mean that epsilon is antisymmetric?
Sorry?
You mean that epsilon is antisymmetric?
Yeah, it's antisymmetric in all indices.
Yeah. So this is essentially how the intention was that you should solve the exercise. I'm just trying to understand how it comes that you didn't have to reverse the order of indices of epsilon, because I had to do that. So let's see, for the first commutator, the index should be j, I, k, and that's what you have. And for the second one, it should be j, I, k, and that's what you have. Yeah. So, right. Yes. Yes, and this looks right. Good. Thank you. Did you write that with your mouse?
Yeah. So
that was impressive.
Okay, thanks.
I have never seen anyone writing that well with a mouse. Okay. Then there is only one problem remaining on this sheet, and this is a problem that requires some creativity / some mathematical insight. So it's about the homomorphism that we have between group SO3 and the group SU2. And it's about stuff that was covered only last lecture. So here I'm not sure someone would have had the chance to solve it. It's a short solution if one has the right idea, but if one doesn't have the idea, one can stare at it for a while. So is anyone volunteering to solve this problem? I would be slightly impressed if someone had managed. Okay, it's not hard if one knows what to do. Okay, so then I guess that I'm solving it. But now I have tried the whiteboard, I have tried the tablet. So now I was thinking I could let you vote. So let's push either yes or no, and then those that doesn't have an opinion can ignore it. So let's vote yes for whiteboard and no for tablet. And we can see. So it was yes for whiteboard and no for tablet. So it's fairly even. The competition is fairly even as far as I can see, and most people don't have a strong opinion. So I take that as it worked about equally well. So we said yes for whiteboard, I think, and there was one more yes. So let's do it the whiteboard way then. So I hope the lighting conditions didn't change much and the angle of the computer seems to be the same. I'm taking the tablet so that I can check the quality as well of the writing. Okay, so in this problem we're considering the homomorphism from last lecture. So we had this homomorphism between SU2 and SO3. As we have seen, the groups are very similar. They have the same algebra. We had that R X was equal to F inverse U of U, F of X, U dagger or inverse dagger, like this. But it's F map X to sigma I xi. So with respect to placement of indices upper and lower, at this point it doesn't really matter because we are not doing special relativity or general relativity. So we can be a bit sloppy. And frequently you see all sorts of notations for placement of indices on sigma matrices, and that applies to QCD as well, that we will come to. Okay, so this is our F of X. And the task is find the general connection between R, I, so the rotation matrix in S3, and U, so the rotation area in S2. So we should derive the formula for R in terms of U, so U in the middle will define an R. So we have spoken about this as homomorphism between groups. And we have said that map between groups is not invertible. But the F is invertible. The one map between R and H2. So we will use that. So since F is invertible, we can write that Rx is F inverse of U and F of X U dagger, which we can then translate to, and now comes inversion, so we invert this side and that side, so we slide F over here and here. So F of Rx is then F, this is just R K J X J. This is the related X equals to X J sigma J U dagger. Sorry, I'm missing sigma here. So this is the related X to be confirmed, okay? So this is the F of Rx. So this was Rx, my argument, nothing in here. And then I take F of X. So I correct between K with sigma K. And here I just apply my F. Now comes the trick. So I'm going to multiply this with sigma, so let's take an unused step. Let's take I. So I have this already here. And now I multiply my sigma I. And I'm doing that over size, and I'm multiplying on that. So this is the same structure, this is just numbers. So if I'm set sigma I can remove all of the numbers. Here, this is already view, it's a matrix. So I insert my sigma I here. And then I take the traces both sides. The point of taking the trace here is that I will have a trace sigma I and sigma K. And they are so under this trace is I is not equal to K. So then taking the trace, I get R K J trace X J trace of sigma matrices, so sigma I, sigma K, this should be equal to trace of this thing here, and here I have sigma I U X J sigma J U dagger. So let's check if this is right. Trace is what I have here. Sigma I U X J sigma J dagger. Yep. Now this trace of sigma matrices, we call it the sigma I, sigma J I, and they are different than the first sigma matrices, sigma J. And sigma matrices themselves are orthogonal, so this is actually if I and K are equal. And if I and K are equal, then sigma I squared. And sigma I squared is proportional to the square divided by the matrix. So this will give me a factor 2 delta K. So now have a little bit to see some more here. Try to be creative. So I have that I here. So my K goes to I. And I have to do. And I don't do anything with this line. And then this stuff went away. So now I have 2R and J and X J. There's nothing but the rotated X is equal to this thing. So collecting the pieces here, I have this R on X is this thing, and on this side, X is also this number. So I can pull my X out again on this side as well. So this means that I divide the R by J in 1/2, dividing out this respective to the other side. Trace. See if that is visible like this. Sigma I U sigma J U. Okay. So what I have is this line. So this is a constant times X.
We can't see the rightmost part of the board.
So any questions in that?
Well, I can't see the last part.
If not, done. Okay, so we have done through all the exercises. So maybe this is, as it stands, this last task is perhaps a bit dry in this homework. It's a bit dry, but it is quite cool because it's related to the fact that when we rotate a particle, we have to sort of rotate it by 4 or 5, come back to the same state if we rotate the fermion, as we have seen in the lectures. The trick then was basically to multiply with another sigma matrix and to take the trace. And so how can one have the idea of making this trick? So either one just likes equations and is good at fiddling around with equations, and then one can come up with a trick. The other way is probably to think about it as a scalar product, because this trace is essentially the scalar product of this trace. And then taking a scalar product to fish out some component is not a far-fetched thing to do, but it's rather natural. Okay, but we are done with this first sheet of exercises. I think we should try to do it better next time. So I will prepare better myself, and I hope that people in the groups will also prepare. And the intention was actually to give you a reason to interact with each other as well. So you can imagine that it's a bit boring to sit in one's own room all the day without talking perhaps to so much people, at least not via the university, at least not as you normally do. As an intention, we had good intentions, which actually we wanted to create some initiative for you to interact with each other and solve the exercises together and to feel a sort of joint responsibility to solve them. And we have seen examples, I think, today that it can work really well. Of course, not everyone has had that, but presentations with pen and paper can also work well. So I hope that next time it will work out slightly better than today. Another comment that I have is that I think presenting scan solution is of course perfectly acceptable. It's the way we have to do it these days because we cannot require everyone to have a tablet or so. To be very skilled with using the mouse. But I think it is quite good that they try to take it quite slow in the presentations because actually we have time here. We have time to do the steps to expand something, even though it's a fairly trivial steps. We can do it, and the intention is that we should see the solutions in their full complexity. And in order for others to follow, maybe people don't follow immediately, but then maybe they take notes, and then it's hard. It's a solution that is just a flash. So I think it's good if we try to present the problems in such a way that it is possible to take notes. Then for the next problem sheet, I have put it online, so you should be able to find it. There's actually one exercise that I added just very recently about the quaternions. This came about because the students asked if there was any connection between the quaternions and the Lie algebras, and it turns out that there is. But what I should also say about this sheet is that I also added comments about what material the lecture notes it depends on. So we are stretching it a little bit in the sense that for that exercise sheet, it's again the situation that there are some problems which depend on some material that is not presented until Tuesday. But either it's very easy stuff, so you don't actually need it to use the lecture. You can just check out some formula and solve the problems anyway. Or it's the situation that you should have seen it in quantum mechanics, and that's the situation for spin addition. And on top of that, it's the page after the page where we stop, so you can just go on and read it. You don't need additional material. Okay. So
I have a question.
Yeah, sure.
The exercise you just presented, how could you divide by xj since there was a sum over xj?
No, it's not dividing with xj. It's that it should be valid for all xj. It should be valid for all vectors.
Okay.
Yeah. But thanks for asking the question. So maybe there are some more questions actually on something else. So yeah, obviously it is harder for people to ask questions when everything is online, and obviously people don't ask as many questions, but then as normally. But feel free to ask questions. So also in the context of the lectures, I don't arrange extra hours where I sit in front of the computer and run and wait for you. I think few people do. And especially since I'm not receiving any questions in connection with lectures, I don't really see the need of it. So instead, before considering arranging special sessions, I would encourage you to ask questions in the context with regular education.
I have a question not directly related to exercises.
Yeah.
I was wondering whether there are any preparatory questions for the oral exam. I haven't found any on the course webpage.
No, we haven't prepared such questions. I know that some students like it a lot, and this is why we have introduced this in a podology course, which you have taken. I personally don't really. I'm not sure that there is anything to gain by preparing such a list of questions. So I think that the feeling that one should get for the course content by studying the course defines the course as well as a set of questions. So we haven't prepared it. It could be that we do it in the future at some point if people really want it, but personally I'm hesitating if it's really helping. When we have such questions, we also have some place that I don't think it's not in the set of questions. Yes, of course. I mean, it's the content of the whole course. So yeah. So any other comments or questions? Okay, so then I guess I see you, most of you, on Tuesday for the 4th lecture. So have a nice weekend and see you then. And if there's a problem with the new exercise sheet, let me know. It could be I try to be creative and come up with new interesting problems, but then there's a risk that they're not clear or that there is a typo. But that's just because I'm trying to make the course better. Okay, so thanks for today then, and well, I'll stay around for a few minutes, but yeah, feel free to leave, and maybe someone has some more private questions, smaller questions.
Thank you. Nice weekend.
Thank you. So we have Emil, Daniel, Edmund, Victor around now. So
Well,
yeah.
if there's no question, see you guys next week.
Yeah, see you. So I say bye then.